Welcome back. In today's video, we're diving deep into one of physics' core subjects. By the end, you'll have a firm understanding of the fundamental principles of waves. We'll break down these key concepts step by step to ensure clarity and comprehension. So, without delay, let's jump right in. There are two distinct categories of waves, characterized by their shape. What's displayed on the screen are representations of these two wave shapes. One category is known as transverse waves, while the other is termed longitudinal waves. Transverse waves resemble the undulating motion seen on water surfaces, while longitudinal waves, akin to sound waves, exhibit alternating compressions and rarefactions within a medium. In transverse waves, the highest point is identified as the crest, and the lowest point as the trough. On the other hand, in longitudinal waves, the compressions and rarefactions correspond to the crests and troughs of transverse waves. It is important to recognize that numerous types of waves can display characteristics of either, or both transverse and longitudinal shapes. These wave types are commonly categorized as mechanical waves and electromagnetic waves. However, there exists a third category called matter waves, which do not adhere to either of these two shapes. Now, let us explore each of these categories in more detail, starting with mechanical waves. Mechanical waves, such as water waves, sound waves, and seismic waves, are prevalent in nature, and propagate exclusively through physical mediums like water, air, or solid objects. Their behavior adheres to Newton's laws of physics, and can be categorized as either transverse or longitudinal waves. The speed of a mechanical wave is contingent upon the properties of the medium it traverses, such as density, elasticity, and viscosity. Electromagnetic waves consist of visible light, infrared and ultraviolet radiation, radio waves, microwaves, X-rays, and gamma rays. Unlike mechanical waves, they don't require a medium for propagation, and always travel at the speed of light. It is worth noting that electromagnetic waves are exclusively transverse in nature. Matter waves deviate from the characteristics of both transverse and longitudinal waves. Matter waves, also known as de Broglie waves, are associated with particles such as electrons, protons, and atoms, and they are crucial in quantum mechanics. Matter waves can travel through space devoid of any medium or material for propagation. Unlike mechanical and electromagnetic waves, matter waves do not represent physical oscillations. Instead, they are described by the quantum mechanical wave function. The phase velocity of matter waves can theoretically surpass the speed of light without violating the principles of special relativity. However, it does not convey any meaningful physical signal or information. Relevant information is solely encapsulated within the group wave, which travels at a speed less than that of light. Consequently, a particle's velocity is determined by the group velocity, not the phase velocity. While this overview provides a succinct introduction to waves, comprehensively understanding the behavior of both transverse and longitudinal waves requires deriving a function that fully describes a wave. I must emphasize that exploring matter waves in depth exceeds the scope of this video. Moving forward, we will focus on delving into transverse and longitudinal waves. In this segment, our focus will be on formulating a comprehensive formula describing a transverse wave. Let's recall our previous derivation of an expression for the perpetual motion of an object, using the angular frequency of a sphere moving along a circular path. We will build upon this groundwork to develop a function for a wave. Before we delve into writing an expression for the wave function, let's revisit the relationship between angular frequency, and period of the sphere. The angular frequency represents the rate of change of an angle. Considering that the angle is a function of time, we express the connection between angular frequency, change in angle, and time as follows. By rearranging this expression in terms of the angle, we obtain the following representation. The time taken to complete one full revolution is defined as the period of oscillation. We can depict the relationship between angular frequency and the period of oscillation as follows. Frequency is the reciprocal of the period, representing the number of rotations per second. Next, we can express the vertical displacement of the sphere using this expression. We can reformulate this expression in terms of angular frequency as demonstrated here. Now, why do we choose to focus on vertical displacement rather than horizontal displacement? Either choice is viable, but when the wave travels in the positive direction of the x-axis, the subsequent elements oscillate parallel to the y-axis. Let's illustrate this phenomenon with an example. Imagine dropping a stone into still water. The resulting ripples exhibit perpetual oscillation primarily in the vertical direction, closely resembling a sinusoidal function, while simultaneously propagating in the horizontal x direction. This is why a sinusoidal function is preferred over a cosine function to illustrate the behavior of a transverse wave. This type of mathematical analysis, which aims to identify patterns or cycles in a time series, is known as Fourier analysis. Specifically, it aims to simplify complex or noisy data by breaking it down into a series of trigonometric or exponential functions, such as sine or cosine waves, facilitating a clearer understanding of underlying patterns or trends. The function displayed on the screen illustrates the vertical movement or displacement of a point on a transverse wave. The duration for one full oscillation of the wave aligns with the time taken for the object to complete a single oscillation. The amplitude, representing the maximum displacement of the wave in the y direction, corresponding to either a crest or trough, equals the magnitude of the radius. This can be denoted as y max. However, this function does not incorporate a variable to represent the position or distance along the x-axis. The waveform depicted on the screen is a visualization of this function, arranged along the x-axis at consistent intervals. Each vertical line in this simulation shares an identical period and amplitude. However, each vertical element in this periodic motion exhibits a distinct phase shift corresponding to its position along the x-axis. Let's rewrite the equation of periodic motion, with a phase shift to describe the distance along the x-axis. This refinement leads us to a function that describes a transverse wave. Since this function is expressed in terms of position x, it allows us to determine the displacements of all elements as a function of time. Moreover, it offers insight into the shape of the wave at any given moment. Now, let's delve into understanding each component of this wave function. It's essential to distinguish between distance and displacement within the context of this wave equation. Distance represents the length the wave has traveled along the x-axis. Conversely, displacement of a wave refers to the height and depth it achieves along the y-axis, denoted as y of x and t. With this differentiation in mind, Ym represents the amplitude of the wave, indicating the maximum magnitude of displacement of the elements from their equilibrium positions, as the wave passes through them. The subscript m denotes maximum, indicating that Ym is always a positive quantity, irrespective of whether it is measured downward or upward. Later in this video, we'll discuss that the intensity of the wave is proportional to the square of Ym. The argument k times x, minus omega times t, is termed as the phase of the wave. This phase varies linearly with time t. For a given wave, this argument remains constant. The wavelength, denoted by lambda, is the distance between two successive repetitive points on the wave, measured along the direction of wave propagation, as illustrated on the screen. It's important to understand that when the wave completes one oscillation, it moves a distance equal to the wavelength. This statement introduces the variable k, which stands for the angular wave number, also known as the wave vector. Alright, let's move forward and formulate an equation to represent the angular wave number. First, let's assume a random position at a distance x1 at time t1. It's important to note that we measure distance along the x-axis, and displacement along the y-axis. The angular frequency, omega, and wavelength, lambda, remain constant regardless of the displacement, y, or distance, x, traveled by the wave. We can express the wave equation as demonstrated on the screen, corresponding to the initial position. Next, let's consider a second position at a distance of one wavelength, denoted as lambda, from x1. We can apply the wave equation to this second point, as shown on the screen. As the wave travels a distance equal to one wavelength, the displacements at these 2 points align, as illustrated in the figure. Given that a wave completes one cycle when it travels a wavelength, let's redefine the distance covered, and the time taken by the wave accordingly. This redefinition results in the following two expressions. Now, let's plug in the values corresponding to the second position, and represent the wave equation as follows. Since the displacement at both instances is identical, we can equate the two wave expressions, resulting in the following expression. Further simplification of the expression leads us to this formula for the angular wave number k. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. In wave theory, it's widely recognized that when a wave travels a distance equal to its wavelength, it completes one full cycle or oscillation. This principle is foundational in understanding wave behavior. To grasp the concept of wave velocity, consider the time it takes for the wave to complete one oscillation, known as its period. During this period, the wave covers a distance equivalent to its wavelength. In physics, speed is defined as the rate of change of distance with respect to time. When applied to wave motion, the speed of the wave is determined by the ratio of the distance it travels, wavelength, to the time taken to cover that distance, period. This ratio quantifies how rapidly the wave propagates through the medium. Now, let's explore the relationship between wavelength, period, and frequency. The period of a wave is the reciprocal of its frequency, indicating that a shorter period corresponds to a higher frequency, and vice versa. Therefore, we can express the frequency of the wave as the inverse of its period. By combining these fundamental principles, we can derive an expression for the velocity of the wave as the product of its wavelength and frequency. This equation encapsulates the essential connection between the spatial and temporal aspects of wave propagation, providing valuable insights into wave behavior across various physical systems. Now that we've gained an understanding of the wave function, let's tackle a few problems to assess our comprehension of the topic. We have a sinusoidal wave, propagating along the x-axis. It has a wavelength of 2 meters, an amplitude of 0.5 meters, and a period of half a second. Our aim is to express the wave function for this wave. The function you see on the screen is the standard form of the wave. In order to define the specific expression relevant to the given wave, we need to ascertain the wave number, k, and the angular frequency, omega. Using the provided wavelength we can determine the angular wave number, k, and using the given period we can determine the angular frequency, omega. Subsequently, by inserting these values into the wave formula, we can derive the expression representing the given wave. We can determine the wave number, using the expression provided on the screen. Since the wavelength is given in the question, we can compute the wave number as pi. Next, let's calculate the angular frequency using this expression. We find that the angular frequency is 4 pi. We now need to determine the phase constant, denoted as phi naught. However, the provided information alone isn't sufficient to determine phi naught, which represents the phase of a wave at time t equals 0 at the origin. Let's consider that the wave's displacement is 0.2 meters when both x and t are equal to 0, and it has a transverse velocity of 5.76 meters per second. With this data, we can calculate the phase constant. Hold on, what exactly is transverse velocity? Transverse velocity refers to the rate at which specific points or components within a wave move at a right angle to the wave's direction of travel. Imagine a wave advancing horizontally along the x-axis. At every point of the wave, there's a vertical oscillation perpendicular to the x-axis. This vertical movement illustrates the transverse motion of the wave. To better understand transverse velocity, let's consider a simple example. Imagine a rope being waved up and down. As the rope undulates, every point along its length possesses a velocity component perpendicular to the wave's direction of motion. This perpendicular velocity component is what we observe on the screen, and is known as the transverse velocity. When we differentiate the displacement function of the wave with respect to time, we derive the transverse velocity function. This function delineates how the velocity of individual points on the wave alters as we traverse along the x-axis. Upon differentiating the transverse velocity function with respect to time once more, we obtain the transverse acceleration. This indicates how the velocity of each point on the wave evolves over time, in the perpendicular direction. Essentially, it delineates the rate at which the vertical motion of the wave is changing at each point. For a given displacement of the wave, we can identify two positions corresponding to the rising and falling edges of the wave, as depicted on the screen. However, the phase constant, denoted as phi naught, corresponds to just one position. To determine the phase constant, let's utilize both the displacement and transverse velocity functions. First, let's substitute values into the displacement function, and derive an expression for the phase constant. Let's denote this expression as A. Similarly, we'll do the same for the transverse velocity function, and derive an expression for the phase constant. Let's denote this expression as B. The angle phi naught should satisfy both equations. However, when solving equation A, we obtain two possible angles for phi naught, as 23.57 degrees, and 156.4 degrees. Yet, only 156.4 degrees conforms to the second expression. Therefore, we can identify the phase constant of the wave as 156.4 degrees. Now, with all the information gathered, we can complete the expression for the wave function. Let's proceed to the next example. We have a transverse wave, represented by the function provided on the screen, modeled on a taut string. Our objective is to determine several characteristics of the wave, such as its amplitude, wave number, angular frequency, wavelength, period, and the speed of wave propagation. Additionally, we need to calculate the transverse velocity and transverse acceleration of the wave element, situated at a distance of 1.4 meters at time 20 seconds. We can represent the standard transverse sinusoidal wave function, as shown. Immediately, we can discern the amplitude, wave number, and angular frequency from this expression. The amplitude is derived from the coefficient of the sinusoidal function, while the coefficients of distance x and time t provide the wave number and angular frequency, respectively. We can utilize the wave number to determine the wavelength using the given expression, resulting in a value of 1 meter. From the angular frequency, we can calculate the period of the wave using the provided expression, which equals 4 seconds. Now that we have all the necessary information, we can determine the speed of wave propagation in the horizontal direction using this expression. By substituting the frequency in this expression with the period of the wave, which is the reciprocal of the frequency, we find that the speed of the wave propagating horizontally is 0.25 meters per second. With this, we conclude the computation of various parameters defining the transverse wave. In the previous example, we derived expressions for the transverse velocity and transverse acceleration. To start, we'll determine the phase of the wave at a distance of 1.4 meters, and at 20 seconds, using this expression. Then, we can substitute the calculated phase into the velocity expression to find the transverse velocity at a distance of 1.4 meters and at time 20 seconds. The transverse velocity of the wave is given as 0.25 meters per second in the positive direction. Just a friendly reminder. When substituting the computed phase value into either equation, it's important to remember to switch the calculator mode from degrees to radians, as the phase is measured in radians. This ensures accuracy in your calculation. We can substitute the calculated phase value into the formula for transverse acceleration and follow the same steps as we did to calculate the transverse velocity. The acceleration is stated as 0.29 meters per square second, but it's negative. This negative sign suggests that the string element is moving in the positive direction, but experiencing deceleration. Alright, I trust you're now well informed with all the details to handle any queries regarding transverse waves. However, before we conclude this discussion, let's work through another example. At a specific moment in time, a particular one-dimensional wave is described by the expression displayed on the screen. After a duration of 10 seconds, the same wave is depicted as shown here. We need to determine the amplitude, wavelength, frequency, speed, and direction of propagation of this wave. Immediately, we can identify the amplitude of the wave from the given two functions as 2 meters, and the wave number as 1.571 radian per meter. Using this expression, we can work out the wavelength since we know the wave number. The wavelength of this wave is 4 meters. We cannot immediately determine the angular frequency of the wave from the given two functions, as was possible in the previous example. To find the angular frequency, we first need to write the wave function. Next, we'll compare the phase of the wave at the initial instant, t1, and express this. We will maintain the same sign convention as in the given instant of the wave. To further streamline the expression, we can substitute the wave number. What you're observing here is the first expression derived from the wave's initial instant. Now, for the second instant of the wave after 10 seconds, we can follow the same approach, while noting how we express time in the expression. After substituting the wave number, this is the resulting expression. However, we can substitute the bracketed component from the above expression, and calculate the frequency of the wave. Which is given as 0.7 Hz. Next, we need to determine the speed of the wave. We can use this expression, which was derived in the previous section of this video. By substituting the calculated values for wavelength and frequency, we can ascertain the speed of propagation of the wave. In the previous section of the video, we mentioned that the phase of a given wave is constant. This can be expressed as follows. It's important to note that although this argument is constant, both x and t are changing. In fact, as t increases, x must also increase to maintain the argument constant. What you see on the screen is the expression of the phase corresponding to the wave given in this example. To find the wave speed, we take the derivative of the expression with respect to time. This provides us with the speed of the wave propagating in the x direction. However, when solving the expression, we obtain the same velocity but with a negative sign. This indicates that the wave is indeed propagating in the negative x direction. With that example, we conclude the discussion on transverse waves. Thank you for watching this video all the way through. I hope these examples have helped you grasp the concepts of transverse waves. In the upcoming video, we will discuss interference of waves and standing waves. If you haven't subscribed already, Please consider doing so to stay updated on future content. Until our next video, take care, and goodbye.